the solution for the IMO shortlist 2017 problem A1. At first, let's have a look on the problem statement. We are given A1 up to AN, K and M, all from the positive integers, such that 1 over A1 plus so on up to plus 1 over AN is equal to K, and the product of the AIs, A1 times and so on up to times AN is equal to M. If big M is greater than 1, we should prove that the polynomial p of x, which is defined as m times x plus 1 to the power of k minus x plus a1 times and so on up to x plus an, has no positive roots. The first thing I want to note is that since we only have to say something about positive roots, we know that x is positive, and so we can say that x plus 1 is also positive and that x plus ai is also positive, since all the ai's are positive integers. Therefore, our polynomial is the difference of two positive terms, and therefore maybe one idea to solve the problem is to find some inequality between these two terms and say that one of the terms is always larger than the other one. To get a better feeling of which of these terms is larger, maybe we should plug in some values for the AIs, K and M, and have a look which of these two terms is larger. Okay, so let's make an easy example. Let A1 be equal to A2 be equal to 2. So now we see that 1 over A1 is 1/2 plus 1 over A2 is also 1/2, so we have that K is equal to 1/2 plus 1/2, which is equal to 1, which is indeed a positive integers. And now we see that M is equal to A1 times A2. This is equal to 2 times 2, which is indeed greater than 1, which is the condition here. Now let's evaluate these two terms here. At first, we have that M times x plus 1 to the power of k is equal to 4 times x plus 1 all to the power of 1, and this is now equal to 4x plus 4. And on the other hand, the second term is x plus a1 times x plus a2, and here a1 and a2 are both equal to 2, so this is equal to x plus 2 squared, and this is equal to x squared plus 4x plus 4. Now, if we compare these two terms, we see that the 4x plus 4 is also here, but in the second term we have in addition an x squared term, and since x is a positive integer, we know that x squared is also positive, and therefore the second term here is larger than the first term. So now our guess is that for each values for a1 up to an, k and m, we have that the second term here is larger than the first term. And if this is really true, and if we can prove this, we are done. So we guess that x plus a1 times so on up to x plus an is larger than m times x plus 1 to the power of k. And now we can plug in the values for m and k and get that this is equal to a1 times and so on times an, all multiplied with x plus 1 to the power of 1 over a1 plus so on up to 1 over an. Now we can isolate the variables, which is always nice in inequalities, and write this as a1 times x plus 1 to the power of 1 over a1 times a2 times x plus 1 to the power of 1 over a2, and so on, up to times an times x plus 1 all to the power of 1 over an. So now it would be enough to prove that x plus a1 is greater than a1 times x plus 1 all to the power of 1 over a1, and then we can factor this inequality for all these n factors and get the desired result. Since the term in the base here is x plus 1, we are motivated to use Bernoulli's inequality. So we can write down that a1 times x plus 1 to the power of 1 over a1 is less than or equal to a1 times x over a1 plus 1. Here we have a less than or equal to sign because we know that a1 is a positive integer and therefore 1 over a1 is less than or equal to 1. This is really nice because now we see that this is equal to x plus a1, which is exactly the left hand side. So now let's have a look where we have equality. There are two opportunities. The first opportunity is that x is equal to 0, and the second opportunity is that 1 divided by a1 is equal to 1, which means that a1 is equal to 1. The first case is impossible since we only have to deal with positive roots and x equals 0 is not positive. Therefore, we only have to handle the second case. Since we multiply this inequality for all indices from 1 up to n, we only get equality here if this holds for every I between 1 and n. So we must have that a1 is equal to a2 is equal to so on up to is equal to an, and this should be equal to 1. So this is the only possible case where we have an equality here. But now, in this case, we get that m is equal to 1, and if we have a look back to our problem statement, we see that we have m is greater than 1, and therefore this is also a contradiction. So we know that in at least one inequality here, if we have a look on this inequality for all ai's, we have a strictly less sign here, and therefore if we multiply all these inequalities, we get the desired result. And therefore we are done.